So this is my lecture 10. So first I will consider internal stability, then I will start digital control. Internal stability of a feedback system. This is very important when you design controller for unstable and or non-minimum phase system. Suppose this is a configuration G. Now suppose your suppose this disturbance is entering, input disturbance, and this is your controller. It is your output. This is your reference input. This is your control input. So now you can see here in this feedback system, whatever exogenous signals are possible, wherever exogenous signal can enter, that I have indicated. This is the so exogenous signal can enter in between the plant, in between the C and G, and in between G and C. Okay. So now the feedback system, this feedback system is said to be internally stable if all the internal signals. So here internal signals means what? Here all the internal signals are stable. Internal signal means what? Here what? Y to R transfer function it may be. It will be. So how many transfer function we will get? Y to R, Y to sorry, R to Y, D to Y, then D to U, R to U. So these are the transfer functions you will get. So here I will consider U here. U I will consider here. Because ultimately D, so R and D are bounded signal. Of course, exogenous signals are bounded signal. Exogenous signals are all bounded signals. So now you can see what is the condition that U by R transfer function all the internal all the internal signals are stable. All the internal signals are, what are the internal signals? So error may be here suppose tracking error may be an internal signal, but tracking error will be stable if Y is stable, because R is bounded signal. Similarly, this control effort to the input to the plant is stable if this U is stable, because D is a bounded signal. So the feedback system, the above feedback system is internally stable if all the transfer functions, that means if the transfer functions, all the element transfer functions, if all the transfer function elements, all the transfer functions function from all four transfer functions, all the transfer functions, okay, all the transfer functions from R to D transpose 2 Y to U are stable. Okay, so how many transfer functions are possible here? So Y by D is possible. So here that means Y to U. Y to U, this is equal to this into R to D. So what is Y by R transfer function? GC by 1 plus GC. What is your Y by D transfer functions? Y by D transfer function is G by 1 plus GC. What is your U by R transfer function? C by 1 plus GC. What is your U by D transfer functions? E by D transfer functions is U by D transfer function is one by one plus GC. U to D transfer function. So U is your output and D is your input. So what is the transfer functions? Well, just 1 minute. And this is Y to R transfer functions is G by, so Y to D transfer function is G by 1 plus DC. U to R transfer function is this one. So now what about your D to U? D to U transfer function is D to U transfer function will also be in that one, right? Just 1 minute. D to U. So this actually should be your G 1 by 1 plus GC. So 1 by 1 plus GC. This 4 transfer function. So here it will be U to D, or this is D is input here. So if you take U D to U, so okay, I will consider U here, not here. I will consider U here, then it will be convenient. So now it is fine. All 4 transfer functions. So that means that is GC by 1 plus GC, GC by 1 plus GC, G by 1 plus GC, and C by 1 plus GC, and 1 by 1 plus GC are all 4 are stable. So this is very important thing, important result in feedback control system. So this is that means 1 plus GC. If 1 plus GC is stable, that means you are thinking that, well, or if you are thinking that R2Y is stable, R2 that means your reference input to output transfer function. If you think that my reference input to output transfer function is stable, that means your system is internally stable. Or if you are thinking that D2Y is stable, then my feedback system will be well behaved. It is not like that. Your feedback system may become internally unstable if any of these 4 transfer function is stable, is unstable. Okay, so here you see whatever these are important feedback configuration. Whatever exogenous signals are possible that I have taken. Nowhere means exogenous signal cannot enter anywhere else. Similarly, wherever output can be tapped, I have taken, because if you tap output from any other point, then the stability, then that output point that tapping point output can be expressed as in terms of U and Y. For example, if I take this error, tracking error, then tracking error can be expressed in terms of y and r. Similarly, here if you take your output here, then again, what is the this output? This output will be u minus d. So since d is a bounded signal, so the boundedness of u will suffice. Similarly, for boundedness of tracking output, your boundedness of y will suffice, like that. So whatever means input output means the minimal number of input output pair, you have to consider that I have input output combination that you have to consider in a feedback system that I have taken. So this is very important result. All four transfer functions must be stable. So these four transfer functions, these four transfer functions must be stable. So what is the this means how to check? Individually we will check. Suppose you have designed one controller, individually you will check whether these are stable. So you need not to check individually. One result is there that the above four transfer functions are stable if and only if it can be proved. 1 plus GC is 1 plus GC is a 1 plus GC, the numerator of 1 plus GC is a stable polynomial. This is numerator, okay, and 2. This is one numerator, numerator of I should write here properly, num, numerator of this one, because this is a transfer function. Ultimately it will have numerator and denominator. Why numerator? Because numerator of 1 plus GC is the characteristics pole polynomial or closed loop pole polynomial. So numerator, it is a stable. So this is necessary. Numerator, this 1 plus GC, numerator of 1 plus GC should be stable. Otherwise, the system will become unstable. Right. So this is necessary. Then what else are required? There should be no unstable. Unstable means, what is unstable? Real of s greater than equal to 0. No unstable pole zero cancellation. In the product GC. This is very important relation. So when you will design controller, there should be no unstable pole zero cancellation between the controller and the plant. If there is unstable pole zero cancellation, then your closed loop system will become unstable. For example, on simple system I will consider, suppose GS equal to suppose your 1 over S minus 1, and CS is equal to suppose S minus 1 divided by S plus 1. Then here what is your TYR? Then what is your TYR? TYR is GC by 1 plus GC. So what will be this? So TYR, it will be 1 by S minus 1 divided by 1 plus TYR. TYR will be GC into S minus 1 by S plus 1 divided by 1 S minus 1 into S minus 1 by S plus 1. So it will nicely get cancelled, and it will be just TYR is what? It will be 1 by S plus 2. So you will think, well, if you give a step input here with GS equal to say 1 over S minus 1 and CS equal to S minus 1 over S plus 1, then if you give a step input here, then output will be very nice. Output will be bounded and it will be exponential, and with steady state value of 0.5. But what is the problem? Where the problem will arise? The problem will arise if you take just y to d transfer functions. If you take just y to d transfer functions, then what will happen? Ty to d. Ty to d is what? On this figure, Ty to d is g divided by 1 plus gc. G divided by 1 plus gc. So this will be 1 by s minus 1 divided by 1 plus 1 by s minus 1 into s minus 1 by s plus 1. This will get cancelled. So it will be Ty to d equal to 1 by s minus 1 into s plus 2. So this implies what? This implies this is what transfer function. So these are unstable. This means Tyd what is unstable, means the feedback system is internally unstable. That means if you give only some state reference input, you will not be able to identify whether the system is internally unstable or not. So if for this system, if you just for the system that I have considered in the example, just if you give a step input, step disturbance input, then you will see the output will divert. That means the system is not internally stable. Okay, so here so the necessary and sufficient condition for internal stability is this one. That means first is numerator of 1 plus gc must be stable. So numerator of 1 plus gc, if you compute g into c, your numerator of 1 plus gc will be what? 1 plus gc, numerator of 1 plus gc will be s plus 2. So it is stable. You may think about it is, well, it is stable, but this is not correct. And the second condition is not satisfied. There is a pole zero cancellation in the product. You can see there is a pole zero cancellation. There is a pole zero cancellation G and C. So S minus 1 will get cancelled. So in fact, so that's why I'm writing. In fact, there is a pole zero cancellation. There is an unstable pole zero cancellation at S equal to 1 in the product GC. This means which makes the system internally unstable, which makes the feedback system internally unstable. Okay, so this is a very important result, internal stability. Okay, so now next we will go to our topic, that is digital control. Digital control system. So digital control systems. Digital control systems is itself is a vast topic. So I will not be able to cover all the things, but whatever is necessary for an undergraduate student, that I will try to say. In fact, a digital control course is there for MTech students if you are interested. That is run in every autumn semester. If you are interested, then you can take this course, digital control system. So nowadays, so earlier what happened? Earlier those lag lead or lag lead controllers were implemented using op-amps, but nowadays those kind of implementation are those kind of analog implementation are in modern control or modern industries. Those kind of analog implementation are not carried out. Those are digitally implemented. All are digital processors are used as controllers. So whatever, so that's why what is the advantage? The whatever control, whatever complex control law is there, you can easily implement. Using a digital processor. So that is the advantage of this kind of digital implementation of controllers. So now the question is how to then if you are implementing a controller using digital processor, so then how to analyze the stability studies, how to analyze the behavior of the system, will the continuous time analysis as we are doing will still hold or not, and how to proceed. So all these things we have to we should know. So that's why this chapter I'll consider the digital control system. Whatever the vast things, but whatever preliminary things are necessary to understand that I will cover. So first I will draw a block diagram of digital control system or sample data. So digital control system here, the main thing is that so the plant is in continuous time model. Plant is continuous time model, and controller is a discrete time controller, or controller is implemented digitally. So that is called sample data system. Another thing is that pure discrete time system may be there. Their plant is also in discrete time. Controller is in discrete time. That is discrete time system. Okay. So I am drawing the configuration of a sample data control system, so which is widely used. This is a reference input. This is a sampler. This is an analog to digital converter. This is your digital processor. Then digital to analog converter. Then your zero dollar hold circuit. Hold. And then your plant. Then your plant. Then it's going to coming to 100. Here have I considered negative feedback? Here I should write negative feedback. So well, so this is your digital controller. So this is a tracking error. So now you can see here ET, continuous time signal, then it is getting sampled. So sampled signal will represent as E star sampled, and this UT, that is control effort to the plant. So now all this sample and hold. So what is done? So the tracking error is sampled, and then the sampled data, sampled signal is converted into a digital signal using the AD converter. Then it is passed to the, then it is sent to the computer, or where the controller is implemented, and then the controller will send the digital signal to the analog AD converter, and then AD converter will send analog signal to the whole circuit, and whole circuit will make it equivalent staircase type of signal or continuous signal, that will be whole signal, continuous equivalent signal will be applied to the plant. So all these operations will be should be synchronized. This is clock. clock should be, so it is not like that they are disjoint, all should be synchronized. So that's why I'm clock, all these are synchronized operation, it should be. Okay, so this is called sample data feedback system. Sample data feedback system. So here plant is continuous time. So this is continuous time. Continuous time. So plant is continuous time. Plant is not discrete. So that is the difference. So here another type of thing you will see, another type of in digital control system. One is sample data feedback system, another is discrete feedback system. Their plant is also discrete domain. That I will come slowly you will understand. So here plant is continuous time plant. Continuous time plant. This is your continuous time plant. Okay. So now, so what is the advantage of digital control system? As advantage of digital control systems. As I already said, that advantage is more reliable, less susceptible to aging and environmental variations. Okay, so it is more reliable system, less susceptible to aging. That means so with the time you will see the op-amp gain may change, right? With after many years op-amp gain, because of some aging, some capacitor, some junction capacitor may change due to change in temperature, due to its due to rust or something, for so many years. So environmental and variation due to aging will not happen, will not affect, that will not happen in digital control system. Why? Because aging in controller, in the plant aging and all these things, effect of aging and all these things will be there. But in controller, if you implement it digitally, those effects will not be there. So this is one thing. Second thing is that digital processors are compact and lightweight. So digital processors are easily nowadays, in terms of ICs, all the things are available. So if you realize a controller using analog way, so many op-amps, amplifiers, all these things, capacitors, many things are needed. But if you want to if you want to implement a complicated controller, complex controller, it is almost impossible using almost impossible in analog implementation. So, but in digital implementation, whatever complex controller is there, you can easily implement. That's why nowadays model predictive control is a very complex controller, but still are being implemented in industry. And this model predictive control is a very advanced controller that is nowadays industries are accepting that controller. So all model predictive controller is implemented using digital processors. So analog implementation is not possible. Predictive based control. So this is that means this is compact and lightweight and less sensitive to noise. Less sensitive to noise, and then And implementation is easy implementation, easy implementation, easy implementation of controllers. So controllers can be implemented easily just by writing a program in maybe C, maybe in any other language, maybe in MATLAB or anywhere. So that kind of language you can use HTML. And there are many things. Yeah. So what are the disadvantage? Disadvantage of digital control system. There are some, of course, some disadvantage. So what is the disadvantage? Sampling. So sampling reduces stability of the system. Sampling is an important. So sampling means sampling you are using your continuous time signal is coming, but you are taking that signal value at some interval. So that's why you are losing some data. You are losing some data means you have to suffer. You have to compromise something. So stability will reduce, and we will see the stability will be dependent on sampling time. So stability will be dependent on sampling time. So so as sampling time is made small, stability increases. That means as sampling time tends to zero, the stability of the discrete time system or the sample data system will converge towards continuous time system. But then the computation cost and all these things will increase. So you have to trade off. You have to choose the sampling time properly. What sampling time is needed for optimal performance? That's the choice of sampling time is an important role for digital control system designers. So now, as you can see, that sample and hold. So these are the very important operation in a digital control system: sampling and hold. So now, how to how to study? So before starting your digital control system, so the sampling and hold operation we have to understand little bit more. So sampling and hold circuit, sampling and hold operation. So sampling and hold operation. So you can see here sampler. So the main thing is that here sampling signals in digital control signals, the continuous times are sampled, and then some operations are carried out on the digital signal, and then again it is hold. So sampling and hold means what actually? That you have to understand. So sampling and hold. So sampling and hold circuit I am just drawing a simple sampler and hold circuit. Suppose your so these are buffer, input buffer, this capacitor, this is your output buffer. So this is your suppose EHT, hold output, and this is your input voltage. Okay, so this is a switch. This is known as sampler. So here output is your E start T, sampler output. So this switch is closed at T interval. So now you can easily see that whenever if your error signal is like this, say, if your error signal is suppose like this, then what will happen? What will be your E start T? E start T will be just at every T interval. Suppose this is 0, this is T, this is T, this is 3T, and so on. 4T, 5T, 6T, and so on. So what will be your output? What will be your E start T? E start T will be, this is your E start T, these values, this dot. So at 2T, E start T will give you this value. Okay. So similarly at 3T, what will be the star value? This one. Similarly at 4T, this one. 5T, this one. 6T, this one. So and so on. And then what will be the hold output? You can see. So this is input buffer. So whatever input you will apply, output will immediately appear. So E start T will be this one then. So this means E start T. Okay. And this is your ET. This is a E start T. E start T. So now what will happen? What will be the EH? So when E start T will, so the capacitor will hold the voltage. So capacitor will be so capacitor will be charged. Capacitor will be charged, and the charging capacitor will be charged, and it will immediately hold the voltage. So what will be your voltage? Suppose 0 to T, 0 to T, 0 to T. So here initial value is 0. So it will remain 0. So then here it will be like this, and then again it will be like this, and then again it will like this, this. So this is your what? EHT. This is a hold out. Okay, so this is your blue color. Blue is your sample. Blue is your actual signal, and then E star, that means green. Green is your this dot are your sample signal, and this red is your hold output, EHT. So this is your sample and hold operation. So that means ET we have applied. So as it is the input buffer, so here voltage will be immediately, here voltage will appear. So that is ET, and then E start T will be this one, and E start T E star t will be this one, and uh, and uh, uh, and once because of output buffer, then your eh will be your just will be just like this. This is 0, then your this much, then this that means uh, your here will be this voltage will be hold, this voltage will be hold here till the next level comes. So here initial voltage was 0. So this voltage will be hold till the next value of voltage will come, and like this. So now that means sampler and hold circuit is represented like this. This is your sampler and then hold. So this is your hold. So this is your E T. This is your E star T, and this is your EH T. So this is sample hold representation. Sample hold circuit representation. Okay, sample hold circuit representation. So there are many things in sample hold. Whatever is needed, that I am just trying to say. The only thing is that this because of this output buffer, this output will held. Output will held constant because of this. So suppose t equal to 0, at t equal to 0, suppose this is 0, t equal to 0, what happens? T equal to 0, E star was 0. So E star was 0 means immediately your output will be 0. Now this output will remain 0 for how long? Till till the switch. So the switch here opens, switch closes at t interval. So switch will close at every t interval. Just at t equal to 0, it will close, and then it will open. Okay, just one pulse. So this is your switch. This I should represent this switch. So suppose this is your pulse switch. Switch just on. This is switch is on. Just here is on. Then here to here is off. Okay, I will not make it complicated. So what I want to say here switch is on. Then from here to here, in between switch is off. Again at t equal to 1 switch is on. Then again off. Then again at 2t switch on. So that's why. So once the switch becomes on, then immediately voltage across capacitor appears. And since just after switch on it becomes off, this switch instantly it becomes off, then that voltage will remain constant because of the presence of this output buffer. Okay, so here, so input buffer because of the input buffer, Input buffer, what is the impedance of the input buffer? So impedance of the input buffer is very high input impedance. So that's why here no current will flow. Here no current will flow. So that is why immediately capacitor will charge. Charging time of the capacitor is almost 0. Okay. So this will happen. So that is the role of similarly output buffer. In case of output buffer, again the current will be here no current will flow here. So because of the high input impedance, so that's why EH will immediately appear here. So now what is your EHT? EH of T. EH of T you can express like this from the above figure. It is E0 into 1 minus E0 is what? 1T. 1T minus 1 of T minus capital T plus ET into 1 of T minus capital T minus 1 of T minus 2T and so on. This means EHT. EHT. EHT will be what? EHT. EHT equal to E0. EHS. If you take Laplace transform, EHS is 1 over S minus. So I want to find what is the transfer function of the whole circuit. So that's why I'm just trying to take Laplace transform of EHT. E to the minus Ts by S plus E of T into 1 by S minus E to the power minus Ts by S, and so it is 1 by S 1 into E to the power minus Ts and so on up to infinity. So then you will get what? EH of S. This is equal to 1 over S minus E to the power minus Ts by S into E0 plus Et into E to the power minus Ts plus E of 2T into E to the power minus 2Ts plus up to infinity. This implies EH of S is what? This is 1 by S minus E to the power minus Ts by S into this you can represent like this. This summation equal of n equal to 0 to infinity E of nt into e to the power of minus nts. See, this is whole signal in transform domain. This is your whole signal in transform domain. Okay. So now if you take what is this summation? Now what is the input of the whole circuit? Input of the whole circuit is the sampled output E star T. So E star T, now what is your sampled output E star T? You can also represent like this. This dot is what? E naught into del T, like that, plus E1 Et into del of T minus T plus E of 2T into del of t minus 2t, because this E0 is, you see, ET will appear only at t equal to capital T. Similarly, E2t will appear E star t equal to E2t only at t equal to 2t. So that's why you can represent like this. This implies what is your E star S? E star S is E0. What is the del t Laplace transform of delta function is 1 plus Et into e to the power minus ts plus e of 2t into e to the power minus 2ts plus up to dot 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 infinity. So this will ultimately imply E star S. E star S equal to summation of n equal to 0 to infinity E of nt into e to the power of minus nts. So this is your sampled signal in transform domain. Sampled signal in transform domain. So from these two expressions then, so this implies ultimately what? Then EHS equal to what you are getting? 1 by s into 1 minus e to the power minus ts into E star s. This implies EHS by E star s. This is equal to 1 by s into 1 minus the minus ts. So this is your whole transfer function. This means g of hs whole transfer functions is 1 over s into 1 minus e to the power minus ts. So this is actually transfer function of zero order hold. So whatever hold operation I have considered, that is transfer function of zero order hold. Similarly, first order or higher order hold is there. Zero order hold means here it will assume constant output in between two signals. This constant in between two sampling. This constant, this constant, this constant. In case of first order hold, what it will do? It will join by straight line. So this is straight line, then again straight line, then again straight line, then again. So first order and higher order holds are more approximate approximate hold version of the continuous time signal. But then other complexities are there. Higher order of the hold will be more, and so many things are there. So zero order hold here, zero order hold means here the output in between sampling instant is fixed constant. Okay, output in between sampling instant is not changed. It is not like that order is zero. Order zero means this transfer function of hold function. So here ultimately it is a zero order, you can also say, because ultimately if you here how will you say it is a zero order? 1 by s into 1 minus e to the power minus ts. So is of what is the order? Order is this is a infinite dimensional system. So infinite dimensional system, if you just take e to the power minus ts, e to the minus ts expansion is if you do e to the power minus ts expansion, in fact e to the power zero order, it will be e to the power minus ts expansion. If you do, it will be 1 minus 1 plus ts minus ts square by 2, then ultimately s will get cancelled. So it is of these are order zero. That's why it is order zero. If you expand it, then ultimately S will get cancelled. So that's why it is called zero order. Order is actually zero, but the functional difference is this one. This is that in between it is constant, and so first order volt it will just connect to, using a straight line approximation it will make, and because the zero order volt so it will make the output constant in between to sample instant. So that is the difference. So zero order is zero order is there here because if you this transfer function, although intuitively it seems it is first order, but it is zero order because if you expand this S will get cancelled, and ultimately only differentiate only it will be that only e to the power minus ts. If we expand, then it will be 1 plus 1 minus ts by factorial 1 plus t square s square by factorial 2 and so on. So ultimately this because of this presence of 1, then 1 will get cancelled, then ultimately it will be of zero order. That means gh of s, if you just factorize, it will be 1. So this will be 1 minus this is 1 minus ts by factorial 1 plus t square s square by factorial 2 and so on infinity, and then ultimately it will be what, t by factorial 1 minus t square s square t square s by factorial 2 and so on up to infinity. This means it is zero order. Numerator no polynomial is there. Okay. So now how to represent? So in digital control we will handle. We will not handle continuous time signals and systems. We will be handling this sampled version of digital control. We will be handling the sampled version of signals. So sampled version of signals, when you will handle, so you have to be, so there is some other treatment. So that is called Z transform. So representation of sampled signal. Representation of sampled signals. So this is Z transformation. How will we, so Z transformation. Okay, so this is caps Z transformation. So this we will discuss. Z transformation, I do not know whether you have studied in transform calculus or not. So anyway, whatever things are needed that I will be discussing. This is your ET, this is your E start T, then again sampler. This is a sampler T second sampler, So now how will you define Z transform? So Z transform will take only when if there is a sampler. Okay. So Z transformation of continuous time signals whenever I am taking, so that means there is a sampler. So Z transformation of ET, this is definition equal to Laplace transform of E start T with e to the power st equal to z. So the Z transform of ET is defined like this. Z transform of ET equal to Laplace transform of E star T with e to the power st equal to z. So this will imply what? Z transform of ET. It is what? It is what is E star T? E star T Laplace transform of E star T. E star t is what? Laplace transform. So now what is your E star t? E star t is now your discrete signal. E star t is this one. Your E naught Et into delta t. So if you take integration, then integration, then ultimately the value will be E0 plus Et plus E2 tt after infinity into Laplace transform. The Laplace transform E star t I have already taken. So it is what? N equal to 0 to infinity Ent e to the power minus nts. So that means summation of n equal to 0 to infinity e of nt into e to the power minus nts. So at e to the power st equal to z. So that means Z transform of Et is what? Summation of n equal to 0 to infinity Ent into z to the power of minus n. Right. So that means this will define as Ez. This is very important relation. Okay. So that means, for example, what is the Z transform of your unit step function? Then, for example, Z transform of 1t. What is your unit step signal Z transform? Summation of n equal to 0 to infinity z to the power of minus n. So this is equal to what? This is equal to 1 by 1 minus z inverse. So this is equal to z by z minus 1. Okay. Well, so now, so this means z transform of 1t is this one. Similarly, there are some properties are there. Some properties I will quickly go through. Some properties, for example, Z transform of f1t summation of two signal f2t equal to, you can define as, you can write f1z plus f2z, where f1z is Z transform of f1t and capital F2z is Z transform. Similarly, Z transform of c into ft, c is any scalar, is c into fz, c scalar. Similarly, Z transform of e to the power minus at ft, this will be equal to summation of n equal to 0 to infinity of minus ant. So just t equal to nt, will put f of nt into z to the power of minus 1. This is as per definition. So this is equal to what? This means z transform of e to the minus at ft. This is equal to, this is what? F of, this you can write like this, f of e to the power of at into z. So ft, what is the ft into z means what? Just z will replace by So suppose the z transform of ft is fz. So z transform of e to the power minus 80 into e to the power minus 80 into ft will be just, you will replace z by fz by fz by f of e to the power 80 into z. For example, suppose z transform of e to the power minus 80 I want to find. What is the, how this happen? So this will be, what is your ft here? Ft is here 1. So z transform of 1t with with z will be now replaced by what? E to the power 80 into z. So now it will be what? This means z transform of e to the power minus 80 will be z by z minus 1. So e to the power z by z minus what is 1 by 1 minus uh, 1 z by z minus 1, that means e to the power of 80 into z divided by e to the power 80 into z minus 1. So this is equal to, you can write z by z minus e to the power minus 80. Okay. So similarly, some other relations are also there. Suppose z transform of cos of beta t, cosine function. So you can easily derive, I am not deriving, z minus cos beta t. Please try to derive z square minus, any standard book you will get all these things, cos beta plus 1 and z transform of sine of beta t. This is equal to z sine beta t divided by z square minus 2z cos beta plus 1. So now another important relation is this one that I will be saying. So z transform of t into ft. So z transform of ft is z, but t into ft. So this is equal to, you can write t into z into dt of fz. So this is important relation. Okay. So how to prove it? You can easily prove it. So what is z transform of t into ft? T into ft will be summation of n equal to 0 to infinity nt. T equal to nt will just put, then f of nt into z to the power minus n. So this is equal to what? Now suppose I want to write like this. So z transform of t into ft. Suppose I want to write like this. dt of z to the power minus n. So dt of z to the power minus n, if you write, then what you have to do, you have to do like this. Here minus z, you have to multiply here n equal to 0 to infinity nt f of nt divided by n. So you can easily verify that this relation and this are same. If we take derivative, then ultimately it will be nt, and this z will get cancelled, because it will be minus z minus n by z, minus n, you are minus n by z. So minus plus minus z to the power minus yeah, z to the minus n by z. So ultimately minus plus, so z also will get cancelled, and also another n will come, so that it will become same. And then then this equation can be rewritten as z to the transform of tft. This is equal to minus tz into summation of n equal to 0 to infinity f of nt into dtz of z to the minus n. This means your z transform of tft equal to minus tz into dtz of, you can ultimately dtz you can take outside because fnt is constant. So dtz of summation of n equal to 0 to infinity fnt into z to the minus n. So this can be written like this: z of tft, this is equal to minus tz dtz of, this is what? This is your fz. Okay. Let us prove, for example, Z transform of T, ramp signal. So what will be Z transform ramp signal? As per this relation, it will be minus Tz into dtz of Fz. What is your Fz? Fz is, Ft is 1. So Fz is dtz of Z by Z minus 1. So it will be ultimately, this will imply Z transform of T. This will be equal to tz by, you can easily verify, z minus 1 square. Similarly, z transform of t square by 2 parabolic signal, it will be just verify t square z into z plus 1 divided by 2 into z plus 1 whole square. So please check it. Okay. So this is about your Z transformation of signals. So now the Z transform of system. The Z transformation of system. So Z transformation of system. Okay, Z transformation of system I will consider in the next class. So just I will see whatever I have taught. So the internal stability of a feedback signal system. Well, and this is your RD bounded signal, bounded exogenous signal, and this is fine. So unstable. So this is very important here. So now digital control system advantages and so on. So sampled hold operation. There are many things, but I have said you in a very shortcut way. Sampled hold operation. So this is the principle mainly. Just some errors. Some signal is coming and signal is going through input buffer. So input buffer will have very high input impedance and low output, very high input impedance and low output. Very high means infinite input impedance and zero output impedance. So that's why your capacitor will what will happen? Capacitor, once the switch closes, capacitor will instantly take that value. Instantly it will charge. Capacitor will instantly charge because here resistance is zero, impedance will be zero. That RC, time constant, is zero. So that's why it will instantly charge, and then what will happen? And then your that capacitor this instantly will charge, and that capacitor charge will will be equal to your hold circuit. So here also another output buffer is given, so that this capacitor again, again will not be loaded. Here input current will be 0. Okay, capacitor, and here again output, that means buffer means your output impedance is 0, input impedance is infinite. With no, here again no discharging current will be there, no discharging, even just the voltage of the capacitor will appear here, no discharging current. Here charging current will flow, but since output has this buffer has 0 output impedance, so here capacitor will not get this discharge, because here input impedance is very high. So that is the principle. That's why this buffers are employed. Okay. I think it is fine. Next class we will continue other things. That's how a feedback system, how a system. Now I have seen how to represent a signal using jet transform. Now we will see if a sampler along with the system is there, then how will you analyze that one using jet transform. So jet transform system we have to understand. Okay, thank you.